right, so does anybody have any questions on that? First of all, can we turn into our homework assignment? Neil? Does anybody have any questions on what we covered last lecture? All right, so I wanted to start today with just a little quote about, since we're going to start talking about feature sizes and what happens in the transistor, both ideal and non-ideal in this section, from if the automobile had followed the same development cycle as the computer, a Rolls-Royce today would cost $100, get 1,000,000 miles to the gallon, and explode once a year. So anyway, so at this point, what we've talked about for CMOS and MOS transistors, we treat them as kind of like these ideal switches. And what you want to do is, like we talked about, there's 0, we're going to activate CMOS transistors, so VDD can go through 1 and so forth. So what we're going to be going into now is talking about what's actually happening inside the transistor and how the physics are affected by width, length, doping levels, and how that actually affects the ability of the transistor to rise and fall. So that's important. So we're going to be going into about that. We're also going to be talking a lot about specific capacitances within a transistor. So in the first section, we talked about diodes and how there's forward biasing and reverse biasing. And the way that occurs is you take a PMOS and an NMOS, PNN type probes, and you just put them together and hook them up to a voltage. Well, now we have all of the gate, source, and drain. We've got your SI, your two glass in between, kind of working as a capacitor there. But we also have diodes between your gate and your body, your source and your body. You've got all of these different elements within a transistor, and we're going to learn about how does that affect the operation of the transistor itself. Because it's speed it up, it's slow it down. In most cases, it slows it down just a little. We're going to learn about different ranges. We're going to learn about the very specific range of a transistor. We're going to learn about cutoff, when it's off. We're going to learn about linear mode, or it's basically the relationship between the channel is going to be dependent on the voltage put on at the drain, sorry, at the source. And then we're going to learn about saturation, or what happens is we reach a certain input voltage level where it's exciting the electrons so much they start colliding with each other, and it actually slows down the electron mobility and the hole mobility. We're going to learn about all that in this section. So the first thing we talk about is just delay. So phase doesn't happen instantaneously. We talked about this perfect switches. So here I kind of alluded to this before. We had this idea of a buffer. A buffer is just two inverters put back to back. And the reason why we want to use a buffer is for timing. We want to make sure that, let's say we have multiple signals, and one of them's 10 nanoseconds ahead of the other. We can insert a buffer to make this signal wait so that way they come on at the exact same time. So now we're going to learn about load capacitance. How does the impact of putting these transistors together impact the ability of the transistor to have an output signal? And then we're going to learn about static leakage. They're not perfect switches, so if we don't have an exact 0 voltage, and sometimes you're going to have instances where this kind of stuff fluctuates, you're actually going to have current going through the transistors when they're supposed to be off. It's going to be a very small amount, but we're going to learn how to determine that. So 2.1 is kind of a review. Capacitance is the ability of a body to store an electric charge. So we have two plates, for example, gate and body, that are separated by some amount, and we're going to learn how that relates to each other. Also, the current relates to the capacitance and the rate of change of voltage over time. So this becomes an impact when you have rising and falling. We're going to learn about that later in this section. Specifically, the amount of time that it takes to deliver, let me read 2.2 again. The capacitance of the transistor relates to the output current using the equation I is equal to the capacitance times the rate of change of voltage over time. So that's dV over dV. So So we have an average current applied, so we're applying an average steady level of current. The rate of change, time required to switch from a 0 to a 1 is defined as time is equal to capacitance over that current times the supply voltage VDD. And then 2.4 and 2.5 are just defining what happens when they're switching and when it's not switching. So it's kind of the statics and dynamics, if you remember that from like engineering fundamentals. Same kind of operation applies here. Static operation occurs when the circuit is not changing voltage, and dynamic operation occurs when the circuit inputs switch. So we're actually going to learn right here, so right below the screen, we're going to have different power consumption voltages, power consumption equations for static versus dynamic power consumption. And later in the course, we'll learn how to treat those, but this is kind of still an introductory how what's actually happening at the transistor level. Last sentence, energy is required to charge and discharge a load capacitance. This is called dynamic power because it's consumed when the circuit is actively switching. So, one of the aspects of this is we're relating this to time, right? So, since the rate of change of power consumption relates to the current, if you have a very quick switch, right, that means your time's going to come down, which means your rate of change of voltage is going to go up. So if you're changing quickly, you're going to bring that time down because your current's going to increase. Now, if you're trying to regulate power consumption, the basic, remember our basic power consumption equation is V equals IR. If you shoot burn it up really fast, guess what? You're consuming a lot of power. And things we have to get really concerned about is power consumption. We want our laptops to work a certain amount of time. We want our phones to work a certain amount of time. If you're sure high frequency is great, but it's a trade-off. And what we're going to learn is that frequency is directly proportional to power consumption. So static power consumption is your classic P equals by V, where it's just P static equals static current. What happens when so you have a rise and you have a steady amount of time where it just stays and then falls. This amount of time where it stays high or stays low, this is static. So the current being consumed by the transistors at any given moment, that's I static, and then just the supply voltage, VDD. The dynamic power consumption is different. We're going to prove this when we get to the next section. But dynamic power consumption is equal to what is known as the load capacitance times the square of the supply voltage VDD times the operating frequency. So this is where our designers have to make a design choice. If you have high operating frequency, that means you're getting quick changes, a high number of changes, so you're going to increase your dynamic power consumption. Also, if you have a lot of changes, you're reducing the amount of time that it's high, which means you're going to have, when we learn about later in the section, if we have a certain amount of time to get from 0 to 1, we're going to learn about noise margins. You have to actually get the inverter or your circuit into that noise margin in order for it to be properly recognized as a 0 or 1. Otherwise, the circuit doesn't work. So you have to have a certain amount of time where it's in static operation in order to guarantee that it actually gets there. The dynamic power consumption is what's happening when it's switching. So here's how MOS works as a capacitor. There's 3 different stages. We're going to call this cutoff, linear, and saturation. First, we're going to have, let's just say the gate voltage is equal to the bind voltage V0. What's occurring is that we just have our negative doped in your positive p-type body, right? So nothing's really, being attracted because here the negative types are kind of being dragged away a little bit. The positive type stores the plus, but everything's they're just the same, so nothing's really moving around here. But now we apply the voltage in the second stage. This below what's known as the threshold voltage. So we have increased it. So now we're starting to bring these positive types up away, right? Down here because we're attracting the negative types. Likewise, the positive dopes start being dragged down because they're going towards the negative type voltage here. So this is what you're creating what's known as the depletion region. And then we're going to reach this magic number called the threshold voltage, where we're actually going to have a higher positive potential exceeding a critical threshold voltage is applied, attracting more positive charge to the gate. The holes are repelled and further, and some free electrons in the body are attracted to the region beneath the gate. So now we've created this what's known as the inversion region. So these are negatively doped. So here we have some electrons, there's some holes, and more holes down here. So we've created an inversion region right at the border of the gate. We've now raised this potential here beyond this what's known as threshold voltage. The importance of the threshold voltage is you need to be able to get that voltage at or above between threshold voltage and VEB in order for the transistors to switch. So once we actually create this, this is when we can start putting the transistors together. So you can see there's actually this kind of range where you apply your gate voltage, you actually have to raise it to a certain amount in order for the transistor to create a channel for it to operate properly. So these are kind of some definitions of that are going to become very important as we start proving equations. So you have gate, source, and drain voltage, as we've already described. The difference between the gate and source voltage is VGS. VGD is gate drain. And then we define this voltage here as VDS, drain source. Now, source and drain are symmetric, but by convention, they have defined that the drain will be a higher voltage, and the source will be at the lower voltage. So we know that for the source, the NMOS body is going to be biased to ground. For PMOS, it's going to be at the supply voltage. So if you apply, let's say we have a CMOS transistor, and we apply this threshold voltage VT to the gate. So now we know that the VGS is going to be the supply voltage minus the threshold voltage. Then we have our output. So what we're having here is we got to apply some sort of threshold voltage with PMOS. And you can tell it's low because we're applying a 0 to get a 1 through, right? So again, we're going to have this different gate drain, and now we're going to have the 1 come through. That's the objective. So we'd formally define the threshold voltage, VT, the minimum gate source voltage that is needed to create a conducting path between the source and drain terminals. So for PMOS, we're trying to get a difference between the supply voltage and the gate. Ideally, you have this 1 at the source and a 0 at the gate. So the ideal threshold is 1 to 0. We're actually going to usually kind of closer to 0.7 times the supply voltage. So if the supply voltage is 1, it's going to be about 0.3 voltage put on the gate. If its supply voltage is 5 just have that same ratio. And we're going to learn that exact value when we talk about going forward. So the 3 modes of operation, we start out, we have either, those scenarios we have earlier, where we have either no voltage or we haven't gotten the gate source voltage to reach that specific threshold, right? In the cutoff, ideally, the drain source voltage is 0. We're going to learn later in this section about instances when the ideal is not the case. And the gate source voltage is less than the threshold voltage. So now, second stage is what we call linear. We have reached our threshold voltage. Gate source voltage is greater than or equal to threshold voltage, and drain source current, the current going from drain to source, or the source to drain, increases. This should be increases linearly with VDS. Technically, that's right, but I want to make sure there's no confusion. Increases linearly with VDS. And then saturation, now we've reached this third place where we're starting to get these collisions. We're going to have all these issues. So the supply voltage, VGS, is greater than the threshold voltage, and the drain source voltage is greater than VGS minus VT. So we have a scenario here where we're an CMOS transistor, right? So we have gate, source, and drain. Source is going to be equal to 0. Ideally, we want drain, so we want the drain is equal to 0, right? So VDS is greater than or equal to VGS minus VT. So what happens? We put a 1 here. So what we want is 1 minus 1, and then 0 minus 0. So these are equal. So what happens when we have an instance where we get 0.1, 1.2, and 0.4 somehow? This can be created through improper doping. This can be created through body biasing. What happens when our body is not equal to 0? We can either do positive body biasing or negative body biasing. Negative body biasing will actually speed up the transistor. Positive body biasing will reduce power consumption, increase accuracy. But 0 tends to be a magic number unless you're doing very unique things with it. So when you have a situation like this, what's going to end up happening is now you're starting to get excited the electrons to the point where it's actually forming transistor operation. So the figure description for a cutoff operation is, so this is a N-type transistor, right? So we have N plus, P-type body. So in cutoff, we have not reached this threshold voltage. So our dopants, our electrons stay in the source and drain, and then our P-types remain in the P-type body. Hey, before I scroll down, does everybody have 2.7 and 2.8? Okay. It's also on video, so technically you all have it. But. So now we reach this linear region. So now we're starting to create this inversion region. And this is where the inversion becomes important, because now we actually have our channel where N types can go through. So by pushing, we've subtracted the P types down, we create an inversion region. Now that we reach a threshold voltage, and we have our channel. Now, the third section is when we get to saturation. Now, saturation, because of the way we are starting, our channel is actually going to decrease a little bit. I'm sorry, this is not it. Yeah, our channel is going to decrease a little bit, and the reason why sometimes we have some parasitic capacitances where you see how we have a plate here, we have a plate here. If we start raising the voltage where VDS is greater than VGS, then it's going to cause this to actually kind of cut off the channel. So that's where our issue happens. So that's kind of a small overview. So we're going to learn a little more about how the currents flow through and the actual physical implications of that. Before I go any further, does anybody have any questions about linear saturation? Okay, so we're going to discuss this concept of channel charge. Recall that the charge of capacitance. Okay, I've already kind of gone over this a little bit, but the important details is we're going to find the average channel potential. And the difference between source and drain. So this is the channel potential. Voltage difference here between here and here. And so since we also know that dVs is equal to dV minus Vs, we can define the channel voltage further as Vs plus Vs plus VDS, because we've now inserted a negative sign. And this becomes Vs, voltage at the source, plus VDS over 2. Does that make sense? So now we're going to figure out all these voltages at the gate. So now, if we know that the gate to channel potential, VGC, gate to channel, is the difference here. So we have this kind of capacitor is equal to gate minus the channel voltage. So now we add voltage at the gate minus this equation that we've just derived here. So to go over this again, just to make this be clear, what we're doing is we're trying to figure out the voltage for the channel to determine the capacitance. So first we have to find the channel voltage. Channel voltage is the difference between here and here. So that's the whole potential throughout the channel. When we find this out, we know that it's just VS plus VD over 2. And we also know that VDS is equal to VD minus VDS. So by substitution, we are able to determine that the channel voltage is equal to the voltage of the source plus VDS over 2. Next, now that we have the voltage of this plate of our capacitor, now we have our gate voltage here, and we have our SiO2 to serve as the thickness, the width between the capacitances. We now know our gate voltage, and we now know our channel voltage. So to determine the difference, we subtract the gate voltage, we subtract the channel voltage from the gate voltage. So that becomes VG minus channel VC, and this is equal to VG minus VDS minus VDS minus VDS over 2. And we could also define VG minus VS as VGS, voltage gate source. So now the voltage of the channel charge is difference between VGC. So now we actually have the difference between our gate charge and the threshold voltage. So now this becomes VGS minus VDS over 2 minus the threshold voltage. So I should mention here before we go on any further, I'm starting to compile a equation sheet that you'll be permitted to use on the exam. My recommendation, staple it to the exam, you can take it off during the exam. My recommendation is your practice problems for your exam. You'll have the exact equation sheet available to you by the time we've done our exam review. You'll have the week to prepare. When you're working on problems that relate to the specific equation or this specific variable, I'll have the constants on here. For example, I talk about the permittivity of free space, like how fast can something travel through air, 8.85 times 10 to the negative 14 farads over centimeters, because we're relating it to capacitance, and we're going to be able to derive the capacitance of the unit gate area because we're going to be talking about width and length. But these equations will be on here. I can kind of show you really quick what I have so far. So I'm starting to put all these equations and variables here. So Q is the charge on an electron. EO is the permittivity of free space. This KOX is the permittivity constant of oxide. We're going to learn about this in a second. But you would multiply 3.9 times this 8.85 to get the permittivity of the oxide. Eventually, we're going to be talking about the permittivity of silicon itself. So you multiply that by 11.7. The thickness of the oxide we define as 10.5 times 10 to the negative 8 centimeters. And we're going to be using all of these variables here in a second to actually determine the gate capacitance per unit area. But when you're practicing these problems, and you can kind of see how this VGS times VDS minus VT is starting to tie into how we determine current. So we're starting to build towards that. EOX, TOX, length, width. And this is our electron mobility. But we'll go over that in a bit. But so I'm starting to build that up so you have that available to you when you're starting to practice for your exam. We define the EO as the permittivity of free space, and we could derive the capacitance of the unit area. So as a note, so how is this permittivity determined? It's the inverse of the constant 4.5 times 10 to the 7 HF per meter 1, and we're multiplying that times the speed of light squared. So if you really want to start digging into this even further than we're going to go into the course, you're starting to get into relativity. So this should be 3.8, not 3.9. It's probably defined on the equation sheet. The permittivity of SiO2 is 3.8 times greater than a vacuum. This is denoted by KOS. And so the equation for determining the capacitance per unit area is found by multiplying the permittivity of free space times the variable 3.8 for SiO2, because that's what's between the 2 plates, right? And then we're dividing this by the actual thickness of the oxide. And that's 10.5 times 10 to the negative 8. And so oftentimes you'll see it defined in this manner, the permittivity of oxide divided by the thickness of the oxide. So the way you would do that is you would just multiply 3.8 times 8.85 times 10 to the negative 14. You get your permittivity of the oxide. The thickness will also be given. And now we have our per unit area equation. So let me read 2.9 again. The capacitance of the unit gate area, CMOS, is found by using the equation CMOS is equal to KOX, which is the constant for oxide, 3.8, times the permittivity of free space, SOX, divided by thickness, TOX, equals the permittivity of the oxide divided by the thickness of the oxide. And so we're going to relate that. Now the gate capacitance is going to be equal to the thickness of the capacitance of the oxide per unit area. So it's going to be divided by nanometer squared times the width times the length. So now we actually have our actual gate capacitance. We scroll down here, we can start. We have our 90 nanometer long transistor, has a gate oxide thickness of 16 angstroms. What is the gate capacitance per micron of width? So if we were doing this and we were using our equation sheet, we have all the equations we just discussed here. We have gate capacitance, COX, WL. To determine COX, we have EOX over TOX. And we have EOX equals EO plus KOX. We know that EOX is 8.85 times 10 to the negative 14. KOX is 3.9. We multiply those together. We divide that by the thickness of our oxide, which is 10.5 times 10 to the negative 8. So now we have COX. So we have this variable. And if we go back, this is precisely what we have done. Now, the gate oxide thickness here is actually given as 16 angstroms. So we multiply 16 times 10 to the negative 8 centimeters. We specifically do this because the unit that is given is 10 centimeters. Angstroms is 10 to 10 meters, but then we divide that by 100 and you get 10 to the negative 8 centimeters. So now we have 3.9 times 8.85 times 10 to the negative 14 divided by 16 angstroms, 10 times 10 to the negative 8. Now, next we have length and width, right? Now, so the phrasing of the question is, what is the gate capacitance per micron of width? We know that we've defined that the width of the transistor, the length of the transistor is equivalent to the size of the polysilicon. So now we know the difference between source and the drain. We use that as our one variable. And then what we're going to do here, per micron width, is to use this particular thing that we have solved to determine precisely how much oxide we want. This is a good way of being able to design your transistor. If you ever get to that level, which we probably won't in this course, but this is a good thing to know for the future. So multiplying it by 90 nanometers times the width is 1.94 femtofarads per micrometer times the width. And the reason we go micrometers is because 14 times 8, that'll come down to negative 7, and through division above comes down to negative 6. And then using our old charge equation, charge equals the capacitance times the voltage. We've now figured out, using our equation here, COX times width times length is going to be our capacitance. And we also figured out that VDC minus VT is going to be our voltage. So taking out that equation a little further, the charge on the capacitor is going to be equal to the permittivity of the oxide divided by the thickness of the oxide times the length times the width times voltage gate source minus VDS over 2 minus the threshold voltage. I'm going to scroll up just a little bit so those of you who are a little further in the back can see. Does everybody have 2.9? So that was equation 1. Let me say example question 2.1. So we're going to start talking about electric field next, and the reason why electric field is important is because it has an impact on electron mobility. It's going to have a real big impact on us when we reach saturation. Because once you have inundated, once you move over too much voltage, applied to drain the source, you're going to have these electrons. You're going to have all kinds of different. You're going to deal with short channel effect. What happens when it's really short, as you can figure out. But electron mobility here, the electric field is equal to VDS divided by the length. So you make that thing really, really small, and since we're trying to use 22 nanometers, 14 nanometers, the electric field, there's some quantum effects that begin to take place. So electron mobility is equal to the equation E equals, electron velocity is equal to the mobility of the electron times the electric field. So then we just plug in our VDS over L there. So we can use our current and linear mode. Now we know that the charge of the channel equal to the length divided by the electron velocity is equal to IDS. So now we start putting in our equations that we did derived before. We put in this equation here for charge that was from 2.10. And now we have the length. And we have that equal to the mobility of the electron times VDS over L. What's going to end up happening is these L's are going to cancel out here. And we're going to end up getting the mobility times the thickness of the permittivity of oxide divided by the thickness of the oxide times the length times the width. VGS times VDS over 2 minus VT times drain source voltage, all divided by the length. So now, this is going to be an important thing to remember. This constant beta here, whenever you see beta in an equation in CMOS, this is referring to this part. Mobility, thickness, permittivity, width, length. It's all together in one variable beta. Yes, Thomas?
What happened to the length of the...
Length, these two lengths cancel out.
Okay.
So then we have this
I
length.
understand. Okay.
Yeah. So then, to simplify it a little further, they're defining this VGT as their gate source voltage minus your threshold voltage, which are these two here, right? So then, the way I'm going to scroll up just a little bit because I see some people cranking their heads. So then this is the final equation. So if the one that's presented in the textbook is this equation here. The supply volt, current from drain source is equal to beta, which we define as the mobility, permittivity over thickness of the oxide times width over length, minus VGT, which we've defined here as gate source voltage minus the threshold voltage, minus drain source voltage over 2 times drain source voltage. So in order to determine the saturation, we just simply know that the channel's pinched off, so VDS becomes 0, right? Here, we're going to get VGT squared. Because now that just means that our gate source and VT apply equally. And I'm pretty sure, I want to make sure 100% certain that I've already included. So you can see I've included beta and I've included VGT. And then cutoff, ideally the current is 0. So this equation here is going to be the next thing you guys see. And there it is. So let me scroll down a little bit. I'm sorry, did everybody get 2.11? Okay. So 2.12, we've now proven all of these equations. So we have our 3 regions. We have cutoff, the transistor is off. Transistor is on in linear mode, meaning we have properly applied all the gates and biases. Beta times VGT minus VDS over 2 times the quantity VDS. And then beta over 2 times VGT squared. For those of you who can't see it, there it goes. We almost made it. Well, halfway through class. So. Great. Unless you, those of you jotting it down, go ahead. Does anybody have any questions on this so far? be counting it down. Cutoff, we have the gate source voltage at 0. All the holes, barriers are in place. Once it starts raising, they start getting pulled away. Once we reach this threshold voltage, we create the inversion region. The inversion region ties to the gate at the source to the drain, creates the channel. What happens is when we reach this saturation region, we end up creating instances where the channel gets pinched off. So we're going to start talking more about IV. So we start IV characteristics. We're going to look at these graphs that have relationships between the current and the voltage for different gate source inputs, and then as the supply voltage goes up, you can see the difference. They actually, you have like, say the supply voltage is 5, you'll get a different plot of gate sources equal to 1, gate sources equal to 2, VGS equal to 3, 4, and 5. And then we'll see the same thing for CMOS, where it actually inverts because it makes sense because they're opposite charge. So I've also included the mobilities on the, or I should have. I'll fix that. Right. So typically the mobility is about half the size of, or the whole mobility is half of your electron mobility. This is the electrons are bouncing through, but the holes actually have to be the result of covalent bonds being broken or created. So therefore, this is why, if you recall on the first day of lecture, I was showing you the layout of the inverter. We have to make PMOS twice as thick as the NMOS. This is why, because of electron and hole mobility. So for the specific process, these are process dependent. So in the case of the AMI 0.6 micron, 120 centimeters over voltage per second. Therefore, P must be wider. In this class, we will assume, unless otherwise stated, that mobility of your electrons over mobility of your hole is equal to 2. Okay, so in this, I think I should, yeah, this is the entire, yeah, that's the entire problem. Okay, so we're going to consider a NMOS and PMOS transistor. So for the first part, consider an ideal NMOS transistor. So we haven't dealt with any non-ideal situations yet. It was a 0.6 micron process with a minimum drawn channel length of 50 nanometers. Let W over L equals 4 over 2. In this process, the gate oxide thickness is 100 angstroms. Estimate the high field mobility of electrons to be 350 centimeters squared voltages per second. So this is mu E at 70 degrees Celsius. The threshold voltage is 0.7 volts. Find the drain source current in cutoff, linear, and saturation mode. Relate the equations to VGS and VDS. Next, given a ratio of mu n over mu p equals 2, find the threshold voltage and a threshold voltage of plus 0.7. Give the equations for cutoff, linear, and saturation mode for PMOS transistor. So we're going to take these equations and derive it. So we already know beta. This is where you want to start. If you recall, all the equations are kind of just based off of beta, right? So now, what we're going to do, we know we are given the mobility at 350 centimeters squared over voltage per second, right? We already know this one. We are given EOX on your equation sheet as 3.9 times 8.85 times 10 to the negative 14 farad over centimeters. We know the thickness is defined as 100 times 10 to the negative 8 centimeters. So we're going to have a TGOs. And we are also given that the width-length ratio is 4 over 2. And that becomes equal to 240 microamperes versus over voltage squared. So now, what you can do is you can go back to the equations here, and now we know beta, and so relate it to VGS over VD squared. So we just plug in VGS minus threshold voltage here into this equation. So this becomes VGS minus VT. And by doing that, we get 240 A over V squared VGS minus 0.7 minus VDS over 2 times VDS. So we have now met the statement in the question, find EDS in cutoff, linear, and saturation mode, relate the equations to VGS and VDS. So we have now done this. So for saturation, it's beta over 2 times VGT squared, which is just VGS minus VT. So again, we divide 240 by 2, we get 120 times gate source voltage minus 0.7 squared. And then the simple way to do this for PMOS is two steps. One, the reason why I mentioned in the question about the different positive signs is we add here because PMOS and NMOS have inverted signs. So, and also since the mobility is divided by 2, we just divide 240 and 120 by 2, so we get 120 over 60 plus 0.7. I'll scroll up a little bit for you, Aaron. So, to combine concepts, if we want the drain source current for both of these to be the same, as we do, we would just multiply the width of the PMOS transistor by 2, that would bring up our IDS to 240 and 1. So that's why we have to double the size of the PMOS transistor. So I know I did have to be on the first day, so now here's math. So here's the plot I was referring to. So here we have drain source current, as a function of drain source voltage. And so each of these plots is what happens when we have a specific gate source voltage. So now we start off, we reach this linear region. So what we want to do is if we want our current to be constant, we have to get to certain drain source voltages, and that's impacted by our threshold voltage. And so I've told you the answer to this kind of hint. Why do you think it looks this way as opposed to just the other way? The second hint, VDS is negative. Yeah. So this is just because the PMOS and the NMOS transistors are oppositely charged. So again, we want these gate source voltages because we're going to have 1, right? And you want gate minus source, you're going to have 0. You want to get closer and closer to the actual difference of the supply voltage. So that way you get the, because if you're putting a 0 on the gate and you want a logic 1 on the source, but on the drain, you're going to need that difference on the source to create the channel. So this is where, so if you actually plot them all out, you'll actually get something like this. You'll get for the NMOS and for the PMOS. In order to get this exact value, you have to multiply the width of the PMOS transistor by 2, or you'll get something that looks more like this. You get something like, and you simulate, and we're going to be learning about spice later in the semester. Okay. So up to this point, we've talked about ideal capacitance, we've talked about ideal current, ideal voltages, and we've talked about linear cutoff and saturation mode. But now we're getting this concept called parasitic capacitance. We have learned C6 here, and now we have to deal with what happens with capacitance between the source and the body, the drain in the body, the channel in the body, gate, drain. So we have all of these different ones. So parasitic capacitance is any capacitance in the transistor, meaning anything that we have not covered up to this point, that is not fundamental to operation of the devices, but impacts certain circuit performance. So what it means is, in order for the circuit to operate, we need to create that capacitance between the gate and the channel in order for there to be a proper amount of charge. However, the capacitances between the differences in different dopants within the rest of the transistor degrades performance. So this is what is known as a parasitic capacitor. So I'll scroll here. So we're going to learn about 3 different types of diffusion. The source and drain's capacitance. Okay, so I've already gone over this. So now this whole idea of diffusion between the different plates, and it's caused by a depletion region with no free carriers forms along the junctions, and that's where you get cut off in your saturation mode. That's a contributor to that as well. The 3 types are isolated diffusion. Isolated diffusion is an instance where the diffusion occurs at one gate and either a drain or a source. So I'm going to scroll back up to the. So you have isolated diffusion here between a gate, a drain, and a source. I also have a larger diagram down here. Let me make sure you can see 2.13 as well. Shared diffusion is where a drain or a source have overlapping diffusion from 2 gates. So you have an instance like an inverter where you have 2 drains overlapping each other. You have to worry about the capacitance, and we'll be learning specifically about load capacitance there as well. And the 3rd type is what's known as merged diffusion. So where diffusion occurs from either 2 gates in proximity to each other. So if you recall, we were drawing our diagrams or state diagrams, we had instances where you can kind of go around here, right? You have one poly here, and you have another poly here, right? And then if you recall the extra credit one, there are multiple cases where this was able to take place. So here, where you have 2 of them next to each other, that's where you can get an instance of merged diffusion. And I'll show you a diagram in a second that's a little more specific than what I just drew. So here, isolated diffusion, you just have a contact that happens to be right next to a poly, and you're worried about isolated diffusion here. Shared diffusion, we say we have A and B, and we have a contact in between. This is where shared diffusion can take place. So where a drain or source is overlapping diffusion from 2 gates. And then merged diffusion is where you have the 2 polys that just happen to be right next to each other, or you have 2 contacts right next to each other. So isolated diffusion is poly gate there. There's a poly in contact. So now what we're going to do, so people were writing. So what we're going to do is we're going to do a detailed MOS gate capacitance model. So we're going to define three types of three gate capacitances that are important here. GB, gate to body. GS is gate to source. And GD is gate to drain capacitance. And for this section, we're going to prove a table down here. We're going to find the gate capacitance initially here as our equation that we presented before, CMOS times width times length. So now we've already accounted for the thickness of the oxide, we've accounted for the permittivity of the oxide, we've accounted for the mobility, width and length. Okay, so now we have what each capacitance looks like as we increase the gate source voltage and how we actually reach this CO. CO is going to be CG. So when we are below 0, it means we're in the cutoff region. So we've reached, I'm sorry, let me start again. Here, we're going to worry about cutoff region first, before we've reached 0 and the threshold voltage in V1. So we're in cutoff. Cutoff, the gate source is dominated by gate body. It dominates below the threshold voltage since the channel is not inverted and the charge on the gate is matched with the opposite charge from the body. So the actual amount of capacitance is still CL as we had before, but it's dominated completely in this table by the capacitance of gate body. So in cutoff region, there is no gate source capacitance, there is no gate drain. We don't have that. We haven't created the inversion region yet. So the second part, we create the inversion region, we reach the threshold voltage, and then the capacitance is dominated by the gate source and gate drain in linear mode. This is because the channel inverts, serves as a good conductive plate. As VGS approaches 1, gate source capacitance and gate drain capacitance approach CO over 2, as you can see in this chart here. So CGS and CGD are both approaching CO over 2, since they represent two pairs of plates. So there, the gate body capacitance goes away, and now we worry about this. They happen to add up to CM, so the amount of capacitance in and of itself is not changed when we reach the desired threshold voltage. Now we're increasing the capacitance charge here. And then what happens when we reach saturation mode? Saturation mode, that's where we start worrying about only the gate source capacitance. And we can kind of see it here as we VDS over VD saturation. The transistor saturates and the channel pinches off. So if you recall from earlier in the diagram, it pinches off at the drain. So now we worry about the capacitance from gate to source. At this point, all the intrinsic capacitance is at the source. Therefore, the charging capacitance approaches 2/3 CO. This doesn't reach a full CO due to the shorter length. So remember, we talked about CO as weight times length. So now we have this channel decreasing due to it being pinched off. So therefore, we are going to deal with a reduced capacitance. Okay, so this table is a good thing to know. A good type of graduate exam question is, I could give you this table and I want you to prove it to me. So basically what I just wrote up here is a good proof type of question. Graduate students will be required. Undergrads can do extra credit on that exam question. But based on TGOs, the extra credit really hasn't been flying off too many labs this semester. Understood. But it is some pretty neat stuff I'm making you read, right? Say yes.
Yes.
There you go. Good grad student. Okay. Don't say drink.
Hey, I told them that they.
You did tell them the truth. Okay, does anybody have any questions on this table before we move forward? This is kind of, if you're viewing this on the video later, a good thing is to kind of look at, this is kind of simulation. So we start out, we're completely going towards a threshold voltage in the transistor. So this is just dominated by gate body. We hit threshold voltages, and then now CGC is going to start, gate channel, but then it's dominated by gate source and gate drain, right? But the gate channel is going to be dominated by the summation of these two. So the blue dot is where, you're adding everything together. So before threshold voltage is completely gate body, and then here it's just this times 2. And then here we're actually at CO, but that's going to start decreasing and decreasing and decreasing because you're pinching off the channel and pinching off the channel. So you get to the point where VDS over saturation becomes 1. Once you approach that, you're approaching 2/3 of your initial charge. So once you hit saturation, you're hurting the ability of the transistor to operate, and you're also reducing channel charge. So I'm going to scroll down here a little bit. We're going to start talking about some non-ideal current voltage effects. Actually, before I do that, any questions on that? I'm throwing a lot at you so far today. So, like, hey, everything switches and now, nope. No, it's not. So we're going to be talking about different concepts here. We're going to talk about velocity saturation and mobility degradation. I kind of alluded to this, what happens when this electric field causes these electrons to start hitting each other. We're also going to be learning about this concept called channel length modulation. When we get that pinch off at the end, how does the actual fact that we're having different lengths, or the length of the width of the transistor, length of the transistor, gotta write that down. As they get closer and closer together, it impacts the charge. So if you have a higher charge, you have higher mobility, they start hitting each other. So all of these issues, as we're trying to get the computer smaller and smaller, we have to deal with all of these things. So this plot is just your normal. So you stop accounting for different types of simulated versus ideal. Now you have the simulated one. This is what happens when you deal with channel length modulation, velocity saturation, and mobility degradation. So we are going to define mobility degradation as reduced carrier mobility as the result of high voltage at the gate of the transistor. As the high gate has the reduced carrier mobility as the result of high voltage at the gate of the transistor attracts the carriers to the edge of the channel, causing collisions with the oxide interface. So here we have our normal mobility. So in this case, we define the mobilities as 540 centimeters times voltage times seconds. And for PMOS, it's 185 centimeters squared voltage times seconds. And the difference is we're going to have 1 plus gate source plus the threshold voltage divided by 0.54 voltage over nanometers times the thickness of the oxide. Again, 1 plus gate source plus 1.5 times the threshold voltage divided 0.338 voltage over nanometers, oxide, the thickness of the oxide. And all of these numbers have been experimentally determined. So these are the equations that are presented in your textbook that are presented in a technical paper. In case you're wondering, right, how did they figure that out? Through simulation. So now we are relating the effective mobility of the electrons and holes to the threshold voltage, the oxide thickness, and the gate source voltage. So this is where, as you're starting to get down to 22 nanometers and 14 nanometers, this is where the thickness of your oxide impacts everything, your transistor length impacts everything, and how the voltages you're using at those different sizes impacts everything. So when your old transistors that you were using for 0.6 micron, 0.25 micron, they're using 5 volts. Your 0.13 micron was using 3.3 volts, and then you're getting down to 90 nanometers, you're at 1.8. 22 nanometers, you're dealing around 0.85 volts as your supply voltage. So you're trying to reduce the supply voltage as those channel lengths decrease because you're got to start worrying about all of these different effects. However, as the channel length decreases, there's fewer, it requires less voltage to be able to activate the channel. So there's pros and cons to everything. Specifically, when we talk about channel length decreasing, we increase the electric field, and we create this concept called velocity saturation. Increased scattering of highly energetic electrons as the result of increased electric field causing high carrier velocity. So if you think about it, let's say you're watching a bunch of kids at a camp, and suddenly you give them all sugar, suddenly they're all bouncing around the walls, and instead of being able to do whatever it was you're doing, suddenly you have to keep them from hitting each other. They're not well behaved like you guys are. It makes it my teaching saturation is I'm teaching saturation because you guys are not on high on sugar or other things don't do that. But as you can see, that if I suddenly extend the analysis, if I suddenly made the room much, much smaller and everybody's crammed together, you're kind of like that, like, hey, this is really annoying. It smells. You know, you want to get away, but you can't. So now you're creating all kinds of other problems. Was there somebody have a question? I'm going to scroll up past mobility degradation. So we're going to be talking about critical electric field and critical voltage. We've already defined the critical voltage is just the electronic field times length, since electric field is voltage divided by length. So the critical electric field and critical voltage using velocity saturation for electrons is 10 to the 7th centimeters per second. And saturation velocity for holes is 8 times 10 to the 6th. The critical voltage is the multiple of the critical field and the minimum drawn channel length. So critical electric field is equal to 2 times the saturation velocity divided by the effective mobility. So you can take the effective mobility, these equations here are 2.17, effective mobility of electrons, effective mobility of holes, multiply that by your saturation velocity, which are given here in the TGO, and you can actually determine the critical electric field. And from there, if you know, you can then determine your critical voltage based on the length of the transistor. So now you can determine specifically what length will cause certain voltage problems and so forth. So now if you're getting to the point where you're going to be one of the people who's trying to figure out how to make all of these transistors even smaller and smaller, you can design it that way. Knowing this is important, especially when we get to concepts of logical effort and buffering, storing, simulation, is knowing how it works at the transistor level when you're putting transistors together will allow you to more effectively take these cells that we're going to be building and be able to ensure that there's proper operation. It's not just enough to put the gates there. You have to make sure that once you're working on the gates together, and then you have to worry about the wires being able to transport a certain proper amount of current in the output and so forth. So all of this builds up. Okay, so it's 12:11. I'm going to stop the lecture here. So up through TGOs 2.19 and was example 2.2. Is that what we just did? Yeah, 2.2. Okay, so here I will not be in. Hey, I'm going to keep the video rolling. I will not be in town on Thursday, so there will not be a lecture, but I will be videotaping the lecture and posting it so you have 2 homework assignments. Aaron's spaceman bro. The range of emotions were fantastic there. So there's that. Everybody, you either email me your feed, the reference off either log assignment or put it here. I will post what I've done for you guys this weekend. You guys are going to be taking, you find your best friend in the class, except you, only undergrads for partners. You're going to be doing the study wiki project. I'm going to give you the directions on how to sign up, so you're going to create a group name on there. And then the next step is you're going to be taking some contemporary issue in CMOS. I'll give you a set of examples. You know, write up a 1,000-word blog post on there. And Daniel Denny, who runs the website, coordinates with all the people from industry, he will be encouraging a lot of these industry people to be commenting on your blog posts. And then what's going to happen at the end of the semester after we take the final exam is the groups are going to come up and present what it is you wrote about, what it is you learned, kind of your experience from that, kind of what you're learning about how, basically what the things we're learning about in class are being used when you go get a job. Grad students will be taking on the last day, Kevin will be select a paper from IEEE regarding CMOS, and we'll be presenting that while you all taunt him by eating pizza. So that's going to be the last week and a half of the course. So I will send out directions on how to do that. I see everyone's itching to leave, so unless anybody has any questions, you're dismissed.